Hi everybody and welcome to the first podcast. So today we will recall what we did last time, means conjugations, and also move ahead with products of even isometries. And finally, we will discuss dihedral groups. So this podcast will go a little faster than the way we lecture in class. So you're supposed to pause every time you don't understand something or hear a question and think about it. Frequently I'll post problems. Sometimes I'll give answers to them, sometimes not. So every time there is a problem, there is a question, you should stop and pause. Sometimes the answer will come after that. Homework, so from now on I'll just ask you to look in the syllabus that is on the blackboard and find the homework there across from the topic that we are discussing. Okay, so let's get started. Conjugations. Well, we discussed how can we conjugate all the various isometries that we are familiar with, from reflections to half-turns to translations and rotations with arbitrary isometry alpha. So remember what a conjugation is. Starting with arbitrary isometry alpha, conjugating, let's say, reflection in line M is just an isometry of the following form: alpha sigma M alpha inverse. So last time we figured out, using the concept, of course, the very useful concept of parity that we introduced for isometries, that the conjugation of a reflection against a line is a reflection against another line, sigma of alpha m. In the same vein, we also saw that alpha conjugating a half-turn with arbitrary isometry just gives another half-turn in alpha of p against the point that is moved by against the new center, which is just the move of p by alpha. And also we have seen that translation from A to B is conjugated into translation from alpha A to alpha B. A little more complicated than that was the situation with rotations. Do you remember what a conjugate of an arbitrary rotation, say with center C by theta, by angle theta? So this would depend, of course, on what? On parity of alpha. So sometimes we have rotation. This is easy to guess. The center is, of course, alpha of C. But then what would be the angle? The angle is either plus or minus theta, depending on the parity of alpha. So plus for even isometries and minus for odd ones. So now that we covered all the possibilities here, why we were concerned with conjugations? Well, we will use that in several places ahead, but first and most obvious application of conjugations is to questions of commutativity. When two isometries of either of these four types commute, and when they don't. So we can easily figure out by just and when they commute with each other or not by just multiplying each of them by alpha. And for instance, from the first one, you can see that alpha sigma m is sigma alpha m alpha. And for instance, if we take alpha to be another reflection, then it's clear that two reflections commute. That's what we've shown last time. Remember, if and only if what is true. So when do two reflections commute? When alpha is another reflection. Well, remember, when the line, if line L, if we write alpha as reflection in L, if and only if L is the same exact line as M or perpendicular to it. Okay, so we also figured out that two half-terms commute if and only if they are about the same center. But for instance, if you have tried some examples from exercise 7.3 after chapter 7, which has various combinations of isometries and of reflections and half-turns and half-turns, that would tell you that two isometries, a reflection and a half-turn, will commute if and only if, care to guess what, if and only if the center of the isometry is, the center of the half-turn is on the axis of the reflection. If and only if P is on M. Okay, so that's as far as conjugations go. Exercise 7.3 gives a perfect dictionary, perfect way to translate from algebraic side this or commutativity to geometric side, how the centers or lines, axes of reflections or centers of half-turns, etc., geometrically positioned with respect to each other, following if and only if the isometries commute. So let's now go to, now that we looked at conjugations, and we also know pretty much everything about products of reflections. And now let's go to more complicated situation, products of even isometries, arbitrary even isometries. So for